Welcome back. So in previous lecture we discussed about the distribution of active fault is important. Along with that, the distribution of the seismic event is also important, and basically we are looking at the historical data. Now whether the historical data what we are using and what has been experienced in the recent past is complete or not, that is again an important question. So this figure usually has been seen or been taken into consideration when we are doing the town planning and all that, and these are all the figures which shows that over the time within the input of the data, this seismic zonation map of India was been revised. So this seismic zonation map has been taken into consideration for the development of the building codes also, because this will tell us that which area will experience more ground shaking as compared to the another one, and with respect to the seismic zones. Because what we were looking in the previous slide, that in Himalayas in the recent in 20th century we had three major earthquakes, 1905, 1934 and Upper Assam 1950, and with this the different seismic zones were been categorized, and even taking into consideration the Andaman region, which is also and vulnerable zone in terms of triggering the earthquakes, as well as the Kutch region. So these are all been marked in red. So in Indian seismic maps since 1962, so the first one, the A, is 1962 edition, and then it came up in 1966 with a slight revision, then 1984 and 2002. So this was before the 2001 Bhuj earthquake. So now what we have, we are following the recent one, that is this one, within 4 seismic zones, where zone 1 has been removed actually. So we have zone 5, we have zone 4, zone 3 and zone 2. So this was revised again based on what the intensity of shaking we experienced because of the 2001 Bhuj earthquake. So the point here is that if you have better data of earthquakes and you have the understanding of the pattern of earthquakes, your map will get revised, and the paleoseismology will play an important role in filling up the gap in terms of the record of the seismic events. So on the left, what we have, the old map with 5 zones: zone 1, zone 2, zone 3, zone 4 and zone 5, and the recent one, that is after 2001 Bhuj earthquake, the expected intensity which was marked for zone 1 was not correct, hence it was been revised. And as you have seen in the previous slide, that since 1962 there were many revisions. Now this revision took place or was been carried out after 2001 Bhuj earthquake, which was experienced by the existing population. But if you don't have any record that exists in the historical chronicles, then you are probably going to undersize or underestimate the hazard related to it. So we have several active zones in India that we have been talking about in some of the lectures. Now the the most important part before we get into the detail of the paleoseismology is to look for the historical and modern seismicity. So, whatever the data is available, we take into consideration to understand the pattern of earthquakes, the distribution of earthquakes, along with that which are in the historical chronicles as well as the modern seismicity based on the instrumentation data. This part we will keep discussing when we are talking about the archaeoseismology part also, but let us see what one can infer based on the existing data. So, this map was published way back in 2000, which shows the distribution of earthquakes, and it can be clearly pointed out that this region, that is the most seismically active region, has hosted many large magnitude earthquakes as compared to the rest of the portion of the Indian plate. Nevertheless, this region has also experienced the earthquakes like Jabalpur in 1997, Latur, Koina earthquake. This was related to the reservoir induced seismicity. Then we have Bharuch earthquake and couple of large magnitude earthquakes in this region, that is your 1819, then 2001 was the recent one, and the 1956. This map was published in 2000, so we don't have the location of the 2004 Sumatra Andaman earthquake. That also was triggered somewhere over here further south of the Andaman Islands. And along with this, what information has been given here is the number of people got killed. Okay, this in the bracket we have the number of people got killed, and in Himalayas, if you see the large number of people got killed in 1905 earthquake, almost around 20,000 people were killed here. And recent earthquake which occurred in Kashmir was 2005, where around 80,000 people got killed. So, along with from the regional tectonics or the global tectonics, we are coming down to the from the global to regional one. If we see, then we have to look at that what are the distribution of faults and what are the type of faults that exist, because this will help us in identifying the pattern of earthquakes as well as the type of earthquakes. And mostly what we have learned in the previous lecture, that this region will mostly host shallow earthquakes, but again we will have different type of earthquakes, in the sense whether we are having thrust earthquakes, we are having normal faulting earthquakes, or we are having strike slip. So, major boundaries that exist on the eastern side is the right lateral Sagain fault system, and then in the portion here, that is in the central part, or maybe you can say along the Himalayan arc, we have mostly the compressional tectonic environment, and we see thrust faults, and we have different plate boundaries, different plate fault system, mainly like Himalayan frontal thrust, main boundary thrust, and main central thrust. And also, and as I was mentioning, that one of the transform fault system that exists in Himalaya is your right lateral Karakoram fault system, and if you come towards the western side, then we are having the Chaman fault system. So, this is we are trying to understand that what exactly is happening with respect to the ongoing deformation between the Indian plate and the Tibetan plate in this region. Okay. So, we have the Chaman fault system in the west, which is left lateral fault system. Then we have Karakoram fault, right lateral. Along with that, we have the deformation, which is indicative of compressional tectonic environment, and some places we also see oblique slip here. And then we have in the eastern side, we have Sagain fault system. So, different type of earthquakes will occur. Of course, in this region we will have comparatively deeper earthquake as compared to what we see in this region. So, we have the ITSZ, that is your Indo-Sangpo suture zone, then MCT is main central thrust fault system, MBF or MBT, main boundary fault system or main boundary thrust system, then Himalayan frontal fault system or Himalayan frontal thrust system we are having. And then we have a few more, that is on this side, that is we are having salt range fault system, and we have Kirthar-Suleiman front fault system is over here. Okay. And then in the frontal part, the boundary between the Indo-Gangetic plain, this whitish part is the Indo-Gangetic plain, and the sub-Himalaya is sitting over here. The boundary between that is marked by the Himalayan frontal fault system or Himalayan frontal thrust system. So, if considering those boundaries, what we see is that very preferred distribution of earthquakes, which includes of different magnitudes, and of course we will see that we have the earthquakes which are occurring in terms of the type, that is either we classify in terms of the depth. We have the deeper earthquakes here, we have shallower earthquakes and intermediate, whereas here mostly we will see large magnitude and shallow earthquakes. Along with that, we will also keep experiencing the moderate magnitude and small magnitude earthquakes. Further, this also shows the distribution, and in one of the slide I was showing that we have few more suture zones which exist, and this is another one which is active, which forms the Narmada zone lineament, and then we have the Kutch region. Now, most prominent large magnitude earthquakes that struck the foothill zone of Himalaya in span of last 100 and 150 years are Shillong earthquake, and then 1905 Kangra, 1934 Bihar, Nepal earthquake, and 1950 Upper Assam. Some of the scientific groups have excluded this from the Himalayan earthquake because this earthquake lies further south of the Himalayan belt. Hence, this has been excluded from the earthquake which is related to the Himalayan tectonics, but nevertheless the overall deformation which is going on between the Indian plate and the Eurasian plate was responsible for triggering this earthquake also. So, based on the information that we have from the historical data or the instrumental data, few zones or the areas have been identified which probably are, or we can say the probability of occurrence of earthquake increases in those regions. Okay. So, for example, 1905 earthquake, 1934, 1950, these are the major earthquakes which were responsible for releasing the stress or the strain which was accumulated in the Himalayan region, and the areas in between are been marked as seismic gaps. Okay. So, you have the central seismic gap that exists between 1905 earthquake and 1934, and then we have another one which exists between the 1934 and 1950. And this Shillong earthquake, which I was mentioning that this was not along the plate margin here, it was south of plate margin. Hence, few research groups have excluded this from this tectonic, and they consider that this were the three major events which ruptured the Himalayan region or the Himalayan plate boundary, and the seismic gap exists. Okay, so this seismic gaps will be the areas for hosting next large magnitude earthquake. So, please remember that what we are talking about, the seismic gaps is the gap between the location of two major earthquakes. So, the central seismic gap which also include the portion of Nepal, and that portion triggered the recent two earthquakes, and that was one the main shock was 2015 Gorkha earthquake. Now, based on the information or the data which was available from the historical as well as the recent seismic events, the theory which came up was that these regions have already released the energy which was available all along the plate margin. Okay. And in between this two, like for example, the energy was released in 1905, the energy was released in 1934, and the energy was released in 1950. So, this area will not trigger earthquake or host earthquake in near future, whereas the areas which are sitting in between these two events are likely to trigger the large magnitude earthquake in near future. Similarly, between these two, this whole area is what we call the central seismic gap. But how far this hypothesis is true, that remains a big question. Now, the question is that which fault or the fault system which we have been talking about, like different fault system in Himalayas, right from, if you start from south and then move towards north, then we have the Himalayan frontal fault thrust system, main boundary thrust system, and then we are having the main central fault thrust system. So, which fault system was responsible for triggering this large magnitude earthquakes? Okay, 1905, 1934, and 1950. So, recent paleoseismic studies, which we will try to cover when we are talking more about details about the case studies and all that, we will talk about that. So, recent paleoseismic studies have helped to some extent to understand that one of this earthquake, that is from 1905, 1934 and 1950, was not triggered on the frontal plate boundary, because we consider that the frontal part is the most active plate margin and most active plate like active fault system, but 1905 was not triggered along Himalayan frontal thrust. So, the question comes as whether still we say that the central seismic gap is between 1905 earthquake and 1934, or the central seismic gap is not the central, only restricted to the central part, but also includes further north region of northwest. So, there comes an importance that where exactly those earthquakes were been hosted, along which fault, particular fault. So, we have, for example, in faults which are sitting here, these black lines are showing the fault lines, and they are the regions which will be responsible for triggering the earthquake in future, and which also hosted the earthquakes in the past, large magnitude earthquakes. So, if we consider that 1905 as per based on the paleoseismic investigation, that this was triggered way far away from, that is far south or north of the Himalayan frontal fault system, then this area still have the strain or the energy available to trigger the large magnitude earthquake as compared to what we have. This were like 1934 and 1950. So, 1934 paleoseismic studies suggest that this was on the frontal part. So, if you combine the existing data, including the historical data like 1955, which was in Kashmir, Srinagar region, and then we have the other earthquakes like 1803. This was in the central part. This is 1803, and few more earthquakes, because this is again 1505. So, again the another paleoseismic studies suggest that the 1505 was along the frontal part. Hence, in that case, this will not be a central seismic gap, but again we need to understand that on which fault this was been triggered. Okay, so the epicenter which has been shown here based on the damage pattern was really the earthquake was triggered in this region, or the earthquake was been triggered along the frontal part. So anyway, taking into consideration all the earthquakes, the existing data, historical as well as instrumentation data, and the paleoseismic data also, these two are coming from the paleoseismic investigation, that is 1400 and 1500. So the paleoseismic investigation carried out along the Himalayan front have indicated that there were two major events which occurred during 1400 AD and 1500 AD. So taking into consideration all these earthquakes which have been plotted with respect to the calendar ages here on the y-axis, and x-axis shows the distribution along the latitudes, then or sorry, this is the longitude we have, and then this distribution shows that there is a gap which exists between this one. So this is what has been termed as central seismic gap. But if we consider these earthquakes, then and this fits well within the central seismic gap. So the question comes that whatever based on the distribution of earthquake, what we have marked the central seismic gap is really the central seismic gap exists or not. But nevertheless, because in this we have not considered the 1505 earthquake in this region. So this may fill up this gap, but then what is the recurrence? Because the if you just see here that this all earthquakes 1905, 1934, 1930, these are all events which have occurred during this. If you exclude this 1897, then all these earthquakes are in 20th century, and this were in the 17th century or 15th century and 14th century. So whether there is a repeat of or the area is sitting quiet because no earthquakes were been triggered in this during this, and that is the 20th century, and these earthquakes which were triggered almost like 400 or 500 years back will be triggered in this region again if we are having the recurrence interval of 500 to 600 years. So again, this is what has been shown here, the distribution of different events based on the historical data as well as the paleoseismic data, and here it marks all the sites which were been studied with the paleoseismic investigation. Okay. So this is in the northwest Chandigarh area, Kalamb, Rampur Ganda, Dehradun region. These are the foothill zones, and then Lal Dank and the Ramnagar area in the central region or central Himalayas. So the question again remains that whether the 1505 earthquake was along the frontal part or not, and if that is true, then again we can say at least that if the 1505 earthquake was triggered here, then it is almost like 500 years no earthquake has been triggered in this one. So if we consider that, then of course this remains as a central seismic gap, as if we take into consideration these events like 1905, 1934, 1950, they all triggered in 20th century. Then why not this region? So another exercise, usually what we do is that we try to look at the historical data, and this is the first step if we have to move ahead in the paleoseismic investigation. So in literature you will find several terms which are describing the earthquake size in terms of small, moderate, large and great, and the magnitude which are been assigned to such terminologies are: the small one is less than 6, and moderate less than equal to 6, and less than 7 magnitude, and large magnitude usually we say greater than equal to 7, and great magnitudes we have greater than equal to 7.8. But usually what we consider here is that these are been categorized as in large magnitude, and the great magnitudes are magnitude greater than or equal to 8.5 or so, mainly the Himalayas. Further, because before the instrumentation came in literature, mostly the damage, or based on the damage, the individual or the respective areas have been classified, that what is the intensity. This is Mercalli, modified Mercalli intensity. This we will talk in the coming lectures, that what what is this the Roman letter indicates. But in literature you will find that there are the words or the phrases which have been written as slide, felt slightly, felt sharp, strong, and so on, and you will also find that the noting of based on the damage has been done, talking about heavy damage or the town destroyed completely. And if you correlate this data with the intensity, then you have the very slight, then the intensity was around 3, but if you are having heavy damage, then the intensity goes above 8. So this also helps us in the back calculating the magnitude. Okay. So like few decades back, Gutenberg they came up with an relationship, empirical relationship, which helped in converting those intensities to magnitude. And one such attempt was been made by us in 1999 from Kutch region, where the very meager data was available. So what we did was that we tried to look at the information which was available in the Indian Meteorological Department, then United States USGS, and then gazetters, the old records of Kutch that was way back, written in way back 1971. Okay. So this we took into consideration, and in this study the non-instrumental data given with only intensity, or the terms like small, moderate, large, and great or slight and strongly felt were taken into consideration. The data obtained was characterized as A, historical non-instrumental data, and B, instrumental data. The earthquake data listed in gazetters shows the historical felt reports. This were based on the reports, the historical reports where the earthquakes were been felt at various locations in Kutch region. And then we also took into consideration the keywords like very slight, severe, very severe, and strong. So this is again the intensity of ground shaking which were been experienced by local people. So based on this, earlier the isoseismal maps were been prepared, and even today we try to classify the areas based on the intensity and the damage pattern, and the intensity mentioned in words were converted first into modified Mercalli scale. So in the previous slide what I was showing, that you are having the terms like slight, very severe, were been assigned the modified Mercalli scale, that is whether it is 3 intensity or 4 intensity or 8. Then further the intensity, that is modified Mercalli intensity I, okay, were changed to ml, that is a local magnitude, using the relationship which was been given by Gutenberg and Richter in 1956. Okay. So this is what we did for the Kutch region, and what we concluded is that we prepared a complete table, and with the appropriate location of the epicenters, we plotted those earthquakes on the structural map. Okay. So this is the structural map or the geological map which we have prepared, and this shows that it appears that the area had experienced several earthquakes ranging from magnitude less than equal to 4 to 8, and the intensity ranging between 3 to more than 10 actually. Okay. So this what we apart from this large earthquakes with magnitude of greater than 5 and less than 6, occurrence of earthquakes with magnitude ranging from 3 to 4, these are all micro earthquakes, were more common in this region, and this is what prompted us and helped us in understanding the distribution of microseismicity. And this is what we prepared the plot, and this is way back in 1999 we did, before 2001 Bhuj earthquake, where we plotted these earthquakes, the micro earthquakes, where the instrumentations were not so intensively deployed in this region, but after 2001 we see that we have very good record of even microseismicity, and that also helps us in identifying the seismogenic faults. Okay. So this is how we do the paleoseismology information, and the microseismicity, or you can say the ongoing seismicity, complements each other in identifying the zones which are going to trigger the future earthquake. Okay. So if you see in the broader sense, the major earthquakes were been plotted when we plotted. These are the fault system: Katrol Hill fault system, Kutch mainland fault system. They are all showing very much preferred orientation, or the alignment, or the distribution along these faults. Okay. And then we have the major fault here, which was responsible, that is a Lebon Fault, which was responsible in triggering 1819 Lebon earthquake. So with this I'll end here my lecture, and will come back in the next one with more details. Thank you so much.